There is a revolution in one area of physics taking place today. It came from the creation of ultra-cold atoms. And there are several laboratories in the United States and in Europe where the real progress is taking place. And one is the Center for Ultra-Cold Atoms at MIT and Harvard. It's truly a bicameral institution. The students go back and forth, they attend each other's seminars and work on each other's experiments. Similarly, of course, with the PIs. So it is recognized as one of the world's leading institutions in this new area. And one of the principal scientists in the Center for Ultra-Cold Atoms is Vladan Vuletic. You'll see why when he explains what he's been doing this morning. Would you start out just by explaining where you came from and how you were trained?
Yes, thank you very much, Dan. Yeah, I was born in Serbia at the time, Yugoslavia, former Yugoslavia, but I grew up in Germany. I studied in Munich, where I did my diploma thesis and my PhD. And then as a postdoc, I came to the US to Stanford to work with Steve Chu on ultra-cold atoms. I became an assistant professor at Stanford University, and a couple of years later came to MIT, in very good part because of the attraction of the Center of Ultra-Cold Atoms and all the excellent colleagues. And I should point out that Dan Kleppner is really the one who started the center that is now going strong for 25 years or so.
Thank you. So now can you explain quantum computing and quantum computers?
Yes, I would like to tell you about, let's call it more broadly, quantum physics with neutral atoms. And I've titled my talk, The Quantum Age, from Bell Pairs to Quantum Computers. And this work, what I show you, was done in close collaboration within the Center of Ultra-Cold Atoms with my close colleagues and friends, Misha Lukin and Markus Greiner from Harvard. Let me tell you the structure of my talk. I will tell you a little bit about entanglement, how it went from a spooky concept, very much disliked by Einstein, for instance, to something that is now applied in experiment rather than just being explored. And then I would like to tell you about how you can do what we call quantum simulation and quantum computation, the first steps, baby steps, if you want, of quantum computation with laser-cooled atoms and so-called Rydberg interactions. Much of it goes back to this famous Einstein-Podolsky-Rosen, what Einstein called the paradox. This is this idea that in quantum mechanics, you can make certain states or certain configurations of particles where you take two particles and somehow both the position and the momentum of a particle are in principle uncertain. So when you make repeat measurements on a particle identically prepared, you will get different results for, say, the position measurement or momentum measurements, but you can make these strange states where for two particles, even though each particle individually is uncertain where you will find it or at what velocity you will find it moving, you actually find that they are very strongly correlated, and that measuring one particle, say the position of one particle, tells you exactly the position of the second particle. So each one individually is random, but somehow the correlations between them are very strong, and the correlations between them can exist in multiple variables like position and momentum. And Einstein really very much disliked it because he said there should be reality. If I separate the particles, there should be reality, and there shouldn't be anything that is kind of fluctuating. And by the way, if these things are correlated over possibly large distances, where does the information reside? So according to Einstein, physical reality was that I can locally predict the outcome of measurement with uncertainty. And for many years, this was regarded as kind of just a metaphysical question with no experimental answers until Bell came along and he figured out a way to actually put what Einstein objected to into a testable experiment. However, before we go there, just let me bring up the citation list of Einstein. So this is Google Scholar, where you can see his most cited work. Let's start from the bottom up. So his 1, 2, 3, 4, his fifth most cited work is gravitational waves, right, that have been observed by LIGO a few years ago. Then his fourth cited work is elektrodynamik bewegter Körper, that's special relativity for you. The third most cited work is Brownian motion, the idea that at a finite temperature, particles are joggling around. The second one is the bei einer Erzeugung und Verwandlung des Lichts betreffenden heuristischen Gesichtspunkt. This is in German. This is about the photoelectric effect. This is the work that he actually got the Nobel Prize for. So not for special relativity, but for explanation of the photoelectric effect. But then his most cited work is, can quantum mechanical description of physical reality be considered complete? In some sense, a very controversial work. One might even argue that, his viewpoint has been proven in some sense wrong, but it's his most cited work. And if you look, this was already a couple of years ago, this continues to be the most cited work just because of the development of all these experimental and theoretical ideas about entanglement, etc. So how was this turned into a measurable question? Well, John Bell had the idea to do this not with momentum and position of a particle, but with spin. Spin, or just two states in an atom that we can label 0 and 1. So the kind of more old-fashioned, maybe up to maybe a decade back, we would call this a spin 1/2 system with 2 levels. But more modern language in the quantum computing concept calls this a qubit or quantum bit because it has 2 possibilities. However, unlike classical physics, where say a bit is in either on one state or the other, quantum mechanically we can be in both states at the same time. We can be in a superposition of states. So actually, instead of being just two points or 2 bits, the way we can represent this is on a so-called on a sphere, where you can be in a superposition. And the way to read this sphere is, say, you define the 1 state to be a vector pointing down, the 0 state a vector to be pointing up, and then a superposition state, say an equal superposition of 0 and 1, but it can have various phases. That would be a state pointing in this equatorial plane. So different directions correspond to 0 + 1, 0 - 1, 0 + I1, etc. So basically the quantum mechanical system, because of this ability of superpositions, is richer than the classical system, and it gets even more rich when you allow for 2 particles. So if you take 2 such spins with each other, then the spins can be pointing in some direction and possibly random direction, but you can make states which are correlated, so that if the spin along one axis if the spin is pointing along one axis, you find this for the other particle the very same situation. And what is in addition in quantum mechanics is, while we can imagine the spin pointing at an arbitrary angle, we can only make measurements on a single system along a single axis. And whenever we make measurements along a single axis, I would say along the vertical axis 0 and 1, or we could also measure in the x-axis, we always get only 2 outcomes. The outcomes are digitized. So the spin, the direction of this vector is continuous, but we always have to digitize the outcome. And then Bell came up with this idea to test Einstein's paradox by basically measure certain correlations between the 2 spins. And this is one of the famous states. And basically, if Einstein is right, then a certain inequality of these correlation factors, so these represent basically measurements on the 2 spins A and B. If Einstein is right, then this particular combination of correlations has to be less or equal to 2, whereas quantum mechanics allows for 2√2, this to be larger than 2 up to 2√2. And so basically, people have performed measurement to test this. And one of the famous measurements is by Alain Aspect, who won the Nobel Prize for this 2 years ago. And he made these entangled states in photons. So basically, he had a source of entangled photons. I'll tell you in a moment how that goes. And then you can measure the spins in this system are now the polarizations of the photons. So you can measure the polarization of the photon along different axes. It can be linearly polarized, it can be circularly polarized. So that's how the electric field oscillates. And then you can make these correlation measurements. And these measurements have clearly confirmed quantum mechanics and ruled out this limit imposed by Bell on Einstein's picture. Maybe just you could ask, isn't it very complicated to make these entangled states of photons? It turns out that you can do this by using atoms that you excite to particular levels. So you put an atom in an excited state that is kind of twice excited, and then this atom can decay, and it can decay via one path where it emits a photon of a certain color, say red, which is right circularly polarized, so the electric field rotates clockwise, and then the second blue photon is left circularly polarized, and this is necessary to conserve angular momentum of the atom. For the experts, I've labeled here the angular momentum. But the atom can also decay on a different pathway where it first emits a negative helicity red photon and then a positive helicity blue photon. And these two pathways are indistinguishable. If you start with an excited atom, go to a ground state atom, you cannot distinguish which is which. And it turns out that this system realizes an entangled state of two photons. And this is where the famous, with this system, the famous Bell measurements were performed. Now, if you want to use these photons to make larger systems, to do quantum simulations, maybe quantum computing, this is very, very hard because photons are easily lost. You can't store them for a long time. You have losses in these systems. They're almost ideal carrier of quantum states, but they are difficult to keep over more than, say, 100 microseconds or so. That's a typical length of a fiber in which they can travel because they're absorbed. And it's also very hard to make photons on demand. In this process that I described before, photon pairs are generated, but they are generated randomly. So it's really difficult to make larger entangled states on demands. And even though there are, quantum computing efforts with photons, in my view, they are really doomed to failure because it's not, there's no known technology that can make, large numbers of photons on demand. Atoms, on the other hand, are more difficult to control initially. Atoms at room temperature are moving around at hundreds of meters per second, but with the advent of laser cooling that Dan Kleppner alluded to, one can actually laser cool them so that they move at the speed of ants or so, centimeter to millimeters per second, and that one can trap them in various traps, including laser traps. And I will tell you about it in a moment. So once that is achieved, then one has a controllable quantum system where quantum states can be stored for a long time. And long time for us means, not for us, but overall the record for long time storage of quantum states is something on the order of 30 minutes or so in certain systems. In our systems, it's more like tens to hundreds of seconds. And atoms can be made to have strong interactions on demand. So let me tell you a little bit about the work of neutral atoms on quantum simulation and computation, as I said, done in collaboration with Misha Lukin and Markus Greider. This is a remarkable quotation from Richard Feynman from 1983. As you may know, Richard Feynman was the first to propose quantum simulators and quantum computers. And he said at Los Alamos National Lab in 1983, now we can, in principle, make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. So these are the two internal states for the spin or for the qubit. That's our input. Then the Hamiltonian starts. The Hamiltonian is just the evolution of the system, how the system interacts. The ones move around, the zeros move around. Finally, a particular bunch of atoms represents the answer. Nothing could be made smaller. Nothing could be made more elegant. If you had asked me, even 10 years ago, I would have said, this is pure science fiction, maybe in 50 years or so. But as I will show you, it's remarkable, how close the systems that I will show you comes to this prediction of Richard Feynman. So how do we control individual atoms? How do we make these atoms, move around in a controlled way, etc.? It all goes back to an experiment now a little bit more than 20 years ago in Paris in the group of Philippe Grangier. At that time, people had already figured out how to laser cool atoms. Basically, you can use the so-called Doppler effect, the fact that, for a moving atom, the frequency of a light beam appears shifted. You can use that to laser cool atoms to temperatures very close to absolute zero, maybe on the order of 100 microkelvin, 100 millionths of a degree Celsius above absolute zero, where the atom moves at these kind of centimeter per second speeds. And it was also known how that light fields, laser fields, can be used to trap atoms. What Philippe Grangier did new in this experiment is he used the tiniest possible laser trap that you can imagine. If you take a laser beam and ask yourself, how tightly can I focus a laser beam using any lens, then you run into the so-called diffraction limit. It turns out that for fundamental reasons, the smallest you can make the beam is on the order of one wavelength of light. And that's what Philippe Grangier did. He focused the laser beam at for wavelength with 800 nanometers roughly to an 800 nanometer spot, so a little bit less than a 1 micrometer. And then he tried to trap atoms in there. And people had done that before, but never in such small traps. And what he saw was remarkable. If he imaged this fluorescence of the atom from a camera, so this atom is being irradiated by light that also laser cooled it, then he saw just 2 levels. So he saw basically a discretized telegraph spectrum, if you want, where there's a lower level, which corresponds basically to the background scatter. This is an empty trap. No atom is present. There's a little bit of light hitting the camera. And then when one atom goes into the trap, there's a higher level of fluorescence that stays stable, in some cases for many seconds. And then the atom seems to disappear again, gets reloaded into the trap, etc. Now, a few remarkable things. One is that you can really distinguish one atom just by the fluorescence level on the camera, that you can see this level, that is a discretized signal. But the other remarkable thing is if you think of atom loading as a random process, then you should sometimes also see 2 atoms and more rarely 3 atoms. And this was never present. Now, people started to understand that what happens in these very tight traps is that whenever you load 2 atoms, they are so close to each other that when they are excited to an excited state, they form a molecule. They basically go on a molecular transition, and then they are lost from the trap. They become invisible and are no longer trapped by this trapping light and are lost. So basically, there's a very, very fast process that you can't see on this time scale that leads to the loss of 2 atoms. And therefore, you have about half the time 1 atom, as you see in this trace, and half the time 0 atoms. And that's where the field stopped for a while, because if you wanted to make this, into 10 or 100 atoms, this would be exponentially bad. It would be, the probability to have, say, 100 atoms at the same time would be 1/2 to the power of 100. So it would almost never happen. And people had ideas that were around in the community, but people just thought it was unlikely to work. And the idea is to use exactly this kind of observation on the camera and real-time feedback to quasi-deterministically prepare many atoms. And so this is what we tried in 2016. So here's a vacuum cell. These experiments have to be performed in vacuum, because if you perform them in air, then there would be molecules, oxygen or nitrogen molecules kicking out the atoms from these laser traps. So we need very high vacuum to be able to trap the atoms for a long time. And this change compared to Philippe Granger's experiment that we did is we did not 1 laser beam trap, but we actually did up to 100 of them. So we took a so-called acoustic deflector. That's a device where you send in a laser beam and a radio frequency with different frequencies. And then you can basically, each radio frequency can generate a beam pointing in a different direction and can make a focus beam, as shown here with just 3 beams, that is controllable by the application of the radio frequency. So you can turn it off, you can change the radio frequency and thus move the beam, etc. And then all these traps were focused on this vacuum cell, and then we looked at the other side on a CCD. And so the basic idea is now some traps will get randomly filled by 1 atom or 0 atoms about half the time, but you can image them on the camera, analyze the picture, and then you can turn off the traps that were empty and rearrange by changing simply the frequencies of going to this device here, rearrange the traps so that this into patterns, or the traps are next to each other. And so in this way, you can prepare n atoms in a chain. Let me show you this for this one-dimensional system. What you see here on the screen, these little white dots, each one is a single atom. A camera can certainly see them. They can almost be seen by eye, in principle, if your eye was dark adapted. But cameras can certainly see them. And then you see also these empty places. There are traps here. There are about 100 traps in this picture, but some of them are randomly not filled. And then what the computer does, it analyzes this image and sorts it, moves the trap around so that we make strings of atoms. And every once in a while, an atom is lost during this process, so the string is not perfect. But much of the time we have, either perfect strings of varying length or near perfect strings with maybe 1 atom missing. This movie has been slowed down by a factor of a few. This happens on the time scale of 100 milliseconds or so. So now you can see we can make 1-dimensional strings of atoms quasi on demand. We tried this with first a few atoms, and then we saw that up to 100, we had no problems doing that. And so now for the first time, we could make, n atoms where n can be, at least a number of 10s to 100s on demand. And this is a picture, how we sorted the atoms. So the top trace is the randomly loaded traps. The traps itself are not visible, but the atoms are visible. Wherever there's a free spot, there's a trap that wasn't filled with the atom, and then these atoms get rearranged. And as you can see here, we can, arrange them into linear 1-dimensional patterns. We can arrange them in pairs, for instance, to do Bell experiments. We can, put them 10 atoms at a time, and down here is shown the picture of the traps themselves. So these are individual atoms that can be now controlled on this time scale. We then, and other groups as well, particularly a group in France by Antoine Brouwys, went quickly to do this in 2 dimensions as well. So you see now random loading of a 2-dimensional pattern of a few hundred traps. And then after sorting, you see the pattern on the right where maybe 1 or 2 atoms are missing. And at that time, we had about 98% filling fraction. So you see the initial loading picture and then the sorted picture after sorting. So we can do 2-dimensional arrays of traps. Actually, the group in France made even 3-dimensional arrays. This was a fullerene-like 3-dimensional system, a cone, a torus, and even here you can see the Eiffel Tower that they built out of individual atoms that are fluorescing. We like the 2-dimensional structure, actually, although 3 dimensions are also interesting because it allows us easy optical access along the 3rd direction, the direction out of the plane here, to address individual atoms if we like. So now we can sort atoms. We can make these individual atoms, but to do interesting things, we need to make them interact somehow. So the question was, can we make atoms interact over a distance? And here, just to give you an idea, the distance scale is a few micrometer. Basically, we can't put the atoms closer than 1 micrometer because that's the scale on which we can control the traps. But we can do any distance between, say, 3 micrometers and tens or hundreds of micrometers. So basically, on a crossed human hair, which is maybe 200 micrometers across, you can fit something like 10 to 100,000 traps. So this is, a tiny system. So how can we make atoms interact over those distances? And this goes back to work done by more than a century ago by Johannes Rydberg, a Swedish scientist, and also Niels Bohr, who Johannes Rydberg studied experimentally or via spectroscopy hydrogen-like atoms with electrons in highly excited state. So if you remember your kind of undergraduate physics or your chemistry, then a hydrogen atom can be in the ground state or the first excited state or the second excited state, and there's an infinite ladder of excited states, and you can go up maybe 50 to 100 excitations. So these are atoms where the electron is quite far away from the nucleus. And really pioneering work was done here by Dan Kleppner at MIT, who studied these Rydberg atoms in the 1980s extensively and provided much of the information that we're using today. So here the electron is very far from the nucleus. How far? I'll give you an idea for the states that we use. The distance between the electron and the nucleus is as large as 1 micrometer. In the hydrogen atom in the ground state, it's 1 angstrom, so 10 to the minus 10 meters. This is 10,000 times larger. So basically, in modern terms, you could take a COVID virus and fit it between the nucleus and the electron, because a COVID virus is only a few hundred nanometers. That's how far the electron is. And what that means is that these atoms are very strongly polarizable, and so they can interact over long distances. Basically, any changes and slight changes in one atom, which we call quantum fluctuations, inducing a dipole in one atom, can have an effect on the second atom just because the electron is so far from the nucleus that even the tiniest electric field will perturb the atom. And so this gives rise to very strong so-called Rydberg-Rydberg interactions. And for similar work, Serge Haroche got a Nobel Prize in 2012. So the idea then is that we take these atoms, we can space them, say, by 10 micrometers. And even over 10 micrometers, which is an easily optically resolvable distance, we can make them interact. And how strongly can we make them interact? We characterize things by a frequency. You can characterize by an energy, but more meaningful is maybe a frequency. The frequencies are typically megahertz to hundreds of megahertz. Why is this important? Basically because that sets the speed of any computation that you can perform. You cannot go faster than the interaction strength in these frequency units between the atoms. But still, these megahertz or hundreds of megahertz means that in principle, a processor speed could approach that scale. And for the experiments that I will show you, this kind of interaction times are maybe on the order of a few hundred nanoseconds, so quite fast. So we can now make basically switchable interactions on demand over these optical resolvable distances between these atoms in an array, simply by shining on laser light or not. How does this work? Well, if the atoms are far apart, further than a characteristic distance that we call the blockade radius, say about 10 micrometers, then we can take a laser to excite an atom from the ground state to the so-called Rydberg state. So this is this high principal quantum number state. and the two atoms will be excited simultaneously because they won't talk to one another. However, if the atoms are closer than the so-called blockade radius, then if you excite the first atom and you try to excite the second atom, there's a very strong Rydberg-Rydberg interaction, so this level gets shifted in energy. So if you try to excite from here with the same laser as you tried before the first atom, the second atom will just not get excited, it will remain in the ground state. But of course, the system is symmetric, so instead of exciting the left atom and keeping the right atom in the ground state, the opposite could happen. The right atom could be excited and the left atom could stay in the ground state. And in fact, what you end up with is a quantum superposition between these two states. And this is one of these Bell states that I talked before in the beginning, one of these strongly entangled states. So simply by taking two atoms, placing them close enough, and then shining a laser on both, you can make a Bell state between the atoms that is, has these strong quantum correlations and entanglement. If you think of quantum simulation, I can write out the Hamiltonian. Maybe for this audience it's less interesting. The idea is just that I have terms that can propel an atom from the ground to an excited Rydberg state. This is this first term here, and I can control that by my laser power and also laser phase. And then there's a term that tells me, did I put the laser on resonance with the transition or off resonance with the transition? I can control that as well. And finally, I have this final term, which is the most interesting term, which is the interactions between Rydberg atoms. So basically, you can think of it, if the atoms are closer than a certain distance, I cannot excite both. I can excite most one. If they are further than a certain distance, I can excite both. So we call this a blockade interaction. So basically, out of two atoms or three or four atoms within a certain blockade radius, only one atom can be excited. And that you can already use to do analog simulation of various optimization problems. So for instance, particularly these graph problems. You can imagine a graph and you can ask yourself, for instance, these graphs, these points say represent, cell phone towers. And you can ask yourself, kind of what is the minimum number of towers that I have to turn on to cover basically a certain distance without having, two cell phone towers be on within the same radius. And so you can then say, for this particular problem, this is the optimum solution. And it turns out that for arbitrary graphs, this so-called maximum independent set problem, the idea is how many vortices can I color in the system without any vortices that are connected by these lines to be, simultaneously colored. That is a hard classical problem to solve. But if you could solve this problem, you could solve problems like the famous traveling salesman problem. What is the best route between cities, say in the US, between a large number of cities without ever touching any city twice, etc. What's the fastest route? So we can encode these problems. Here shows you, for instance, a particular graph that we made. Each of these dots is an observed atom, and each of these connections represents a Rydberg blockade. This is also shown by a circle. So basically, if we excite this atom in the middle, then we cannot excite any of the atoms nearby. And then we can excite another atom and then not excite any of the atoms nearby. And now the goal for this mathematical problem is what is the maximum number of atoms that I can excite in this pattern, given this constraint that I'm not allowed to excite any atoms that lie within a circle of each other. And what you see on the right is the solution to this pattern. This is the maximum number of steps. And so we compared here a classical computer and this analog quantum simulator to each other and to see whether there would be a difference. And what we found is that there was a speed up for basically the quantum system over the classical system. But the speed up was modest. The speed up scaled only with the square root, was basically a square root speed up. So, if you make the system, say 100 times larger, then the quantum system performs 10 times better than the classical system. So while this is interesting, it's not really that useful just because classical computers are so powerful, have so many bits and have, such fast speed that, you couldn't realistically beat with a quantum system any classical system of this kind. But nonetheless, it shows that in principle, quantum systems can outperform classical systems. But you can make, many more interesting experiments. You can basically, arrange these atoms in various patterns and then ask various of these quantum simulation questions. And my friends Misha and Markus and I, and together with some other people, founded a company here in Boston And this company put such a simulation machine on the quantum cloud of AWS, of Amazon. So since 2020, since 2022, people at various universities around the world have been remotely accessing our Boston-based machine, basically programming different patterns and performing different experiments on this quantum simulator. So it can be used very much like a classical cloud computer is used. Now, these are analog systems. I would really like to tell you about digital quantum machines, because this is the field that is best understood and what people are most excited about. This is what, what people mean when they talk about quantum computers. I was shocked that even on the debate yesterday, quantum computing was mentioned as one of the areas. You never know what to think if the government gets involved, but let me tell you about quantum computing. So the idea is that in classical computing, you have the famous logical gates or Boolean gates, the AND gates, the OR gates, etc. And you can use these logical gates to, for instance, perform calculations. In quantum physics or in quantum gates, there's something similar where I can take states of two atoms, indicated here by 0 and 1. So the first column is the first atom, the second column is the second atom. And so let's just classify them as these possibilities 0, 0, 0, 1, 1, 0, and 1, 1. And then you can map them into another state. And for instance, this is a famous controlled NOT gate. So it's basically the state of the first atom controls the state of the second atom. Basically, if the state of the first atom is 0, then the state of the second atom doesn't change. So 0, 0 goes to 0, 0, and 0, 1 goes to 0, 1. But if the first atom is in the 1 state, then the state of the second atom flips. So 1, 0 turns into 1, 1, and 1, 1 turns into 1, 0. And it turns out that this gate is so-called universal. So if you can implement this gate together with rotations of individual qubits, then you can make what is called a universal quantum computer. A machine that can do anything what the quantum computer can do. And for instance, if you take a first atom in a superposition of 0 and 1, as shown down here, so basically you prepare the first atom in the superposition of 0 minus 1, and then act for the second qubit starting in state 0 and act on this, you can see that you make this 0, 0, minus 1, 1 state, and this is one of these famous strongly maximally entangled Bell states. So C0 gates can make entanglement, for instance. So how do we make these gates? As I said, we use Rydberg interactions, pioneered by Dan here at MIT. So first, let me tell you about single qubit rotations. So to confuse things a little bit, we actually don't use 2 levels, we use 3 levels. So when we want to store qubits, we store them in what we call hyperfine states. These are electronic ground states that differ only basically by the direction of the spin of the nucleus. And these states are quite long-lived. In our system, for instance, the coherence time can be several seconds. So here, this is the system in which we can store quantum information, but these states don't interact. However, if we take one of these states and excite it to a Rydberg state, then the atoms start to interact. So simply by shining on this blue laser light, we can control the interaction. So first of all, we need to be able to control, to basically turn 0 into 1 and vice versa, and also go to any superposition of 0 and 1. And so these blue oscillations or red oscillations laid down here show you how well we can do it. So you see we have a high degree of control where we can flip an atom from 0 to 1 and back many, many times without losing much signal or much contrast. So this is one of the preconditions for quantum computing. And this was a few years back, and the later results is now basically we can have errors for this flipping of a single qubit that are on the order of 2 times 10 to the minus 4. So we can do something like 5,000 rotations before we incur an error. The other thing that you need to do, which is a little bit harder, are these 2 qubit gates. So basically the ability to make this Bell state, as I described to you before, by this so-called C0 gate. And there we had fidelities of 97%, so about 2% error. And sorry, the slide doesn't show up here, but our latest results are 99.5%. So still, there are errors in the system. And now I want to tell you in the last, few minutes about, an idea that, I find really remarkable, one of the, great theoretical concepts of quantum physics, and that is the idea that you can actually correct errors on a quantum computer. So as you may know, in classical computing, this is well known. How do you correct errors? you encode the same information. We will call that a logical qubits in several copies, or logical bit and physical bits. So basically, simply by encoding information redundantly, you can make the error probability exponentially small, right? So if I encode here, for instance, in a system of 9 bits, information as blue or red, as white or red, and I start out with the white state and maybe 2 of these atoms flipped, I can just say, well, what is the state of the system? Well, 2 are red and the majority is white, so probably the state of the system is the white state, or say the 0 state. And then I can simply flip these 2 bits back. And you can easily see that each time I add 1 more bit to the system, make this, kind of storage a little bit larger, I win by another factor in whatever the error probability is. So this basically, we can make error probabilities exponentially small. Now, in classical physics or in classical computers, that's relatively easy. You can just look at a bit and says, okay, say 7 of them are 0 and 2 of them are 1, so probably they should all be 0, and I'm flipping back the 2. In quantum physics, that's not possible, because as soon as you look at any bit in the system, you're actually destroying the quantum system. You look at the bit, or the environment looks at the bit, you don't know whether it's in 0 or 1 anymore. So all the magical properties, all this entanglement, the magical properties of quantum physics are destroyed by looking at the system. So you can't look at the system. So how can you possibly correct errors if you're now allowed to look, if you're not allowed to look at the states of the qubits? And this is really something very remarkable. The theorists figured out already, starting 2 decades ago, that there are ways of looking at the quantum system and telling whether the atoms are in the same state or in different states without actually ever revealing what state the atoms are in. And one famous example of this is a so-called surface code. So basically, in this system, half of the atoms, the white atoms, are used to encode information. So basically, this whole system is supposed to encode 1 logical bit by many copies of the logical qubit. And this is encoded in these white atoms. And then the black atoms are used to measure whether the white atoms are in the same state or not. So for instance, this black atom here, you can perform quantum gates between this black atom and 4 of its white neighbors. And afterwards, you can read out the black atom, and you will find out, are the 4 white atoms in the same state, or are they in different states? But you will never learn which state they're actually in. You will just compare the state between the four white atoms. So for instance, if this white atom flip had an error, then what would happen is that the 4 neighboring bits would flip. And then you would say, oh, if these 4 actually light up, then I know that the error must have occurred in the middle. And so this is one way, and without ever actually knowing what the state was. And then what do you need to do? You just need to flip this red atom here in the middle without ever knowing its state. Now, these codes have the property, you see, you're adding a lot of complexity. So if you have errors in the individual operations, then in principle, or in most cases, when you instead of using 1 atom, you use many atoms and have to perform all these gates, you're making the system worse. But what the theorists figured out is that if your errors are below a certain threshold, and for the surface code, this threshold is 1%, then actually, as you grow the system and make it larger, your system becomes better, not worse. And it becomes just like in the classical system, exponentially better. That's the main idea. And this threshold for this code is at 1%, and our errors, as I told you before already, are now at 0.5%, so we are in principle below the threshold. Let me tell you about one other features that we can do. So we can entangle pairs, so we can make entangled states of atoms, and then simply by moving the laser beam, we can transport the atoms and then bring them back for checking the entanglement. And what we found is that the entanglement didn't really suffer even if we transported them, to, say, in this case, hundreds of micrometers distances between them. So we can entangle atoms, we can transport them into a different place and then entangle them again with other atoms. And so that allows us to make different geometries of atoms. For instance, by moving the atoms, we can encode, even though we are working always in 2 dimensions, we can encode effectively this 3-dimensional geometry of a torus, where we can start to correct errors. And just to show you in a movie how this is done, you will see stationary bits. These are the bits that are used to read out errors. And then you will see moving bits. These are the data qubits. And then whenever this red circle appears, that's when we apply a laser beam to entangle the atoms that are nearby. So we place the atoms at first like this, we entangle them with this laser beam, then we move them over, we entangle them again, 3rd entanglement, fourth entanglement, and then one all the way around the torus, fifth round of entanglement. And then we move the data bits over here. And then we can look at these syndrome qubits, these qubits that tell us whether any errors occurred, and we can compare them to the errors that actually occurred. And so what we found is that in the system, and these are the data, I won't go into details, but basically we can correct errors to nearly 100% in the system. We can detect and correct errors. Now, of course, you have to make this work not just once, but many, many times in the feedback loop, and that's what we're working on. So there's this kind of vision that we will have actually now more than two zones, one zone where we entangle the atoms, another zone where we store the data qubits, and then there will be, for instance, a third zone where we read out the qubits. But this will be the new geometry. And just to show you what can be done with a state-of-the-art system from this year, here we have many, many physical qubits, a few hundred, and we use them to basically implement logical qubits in the system. And so what we've shown here is as we grow this surface code to larger and larger systems, the logical error actually shrinks. So even though we are performing many more operations in the system, we are shrinking the logical error. It's at the moment still modest. The logical error is a few percent. But as we improve both the physical errors and the size of the system, we think that we can go much lower. So this is, and Google last week also put out a paper where they did something in their superconducting system, also with the surface code, where they showed that as the system grew bigger in their superconducting systems, the logical errors scaled down. Maybe I'll just show you some other movies where we do some other types of gates, again, by moving the atoms and applying laser beams to entangle them, etc. In this case, for the experts, we're making a maximally entangled so-called GHZ state of several logical qubits. Now we have started basically to work with logical qubits, and you see, the control that is possible for these atoms to finally read them out. And this is the most complicated code that we have made so far. This is a system of 12 logical qubits. Here I'm not showing whenever the atoms are close, we perform Rydberg gates on them. And you can see how things work largely in parallel in these structures, where we can basically encode these whole things. In this case, the logical qubits are encoded on these hypercubes of each consisting of 8 atoms, and you can kind of see that these atoms move in groups of 8 or 16 or 32, etc. So maybe, to the end, where are we as a field? We are entering the era of first algorithms with logical, that is error-correct qubits. The improvements are moderate still, but we think we know how to go forward. There's a path, at least in these neutral atom systems, towards large quantum simulators and possibly quantum computers. So the record on the physical qubit number is now held by a group at the moment at Caltech by Manuel Andres. He has trapped 5,000 atoms, or 5,000 physical qubits, and rotated them. Still has to do 2 logical gates, but basically we are in the thousands now. I think 10 to 100,000 physical qubits we know how to do within the next 1 to 2 years. It mainly involves scaling up laser power, scaling up our microscope objectives, etc. We have also performed first experiments with up to 48 logical qubits. It's pretty clear to me that digital quantum simulators will be used for science, and I predict that within say 2 to 3 years, we will be at the level of 100 logical qubits with errors on the order of 10 to the minus 5, 10 to the minus 6, so small errors. You may have heard about the famous Shor's algorithm, which is basically prime factoring. And Shor in some sense started this field by proving that if you had a quantum computer and you had this problem of factoring a large number into prime factors, which is the basis of all encoding on the internet, for instance, that a quantum computer could perform this in exponentially improved time over a classical computer. We are still far away from Shor's algorithm. For Shor's algorithm, you need a few thousand logical qubits, and you need errors on the order of 10 to the minus 12. But once we enter this era of exponential scaling, it's not around the corner, but I think there's a path forward. But with 10 to the minus 6 errors, you can already do a lot of kind of science applications where you simulate quantum systems with these quantum computers. And with this, I would like to end, and thank you for your attention.
So about a year and a half ago, Nuno Loureiro, the new director of the Plasma Science and Fusion Center, had given a talk about kind of work that was going on at the Plasma Science and Fusion Center to enhance the probability of getting a fusion reactor for power production. And he mentioned that quantum computing might be useful. He didn't really go into details about how it could be useful. What I see is, in terms of instabilities and things of that nature, have you discussed any of the possibilities of application of this kind of a system with the fusion people, basically?
That's a very interesting question. I personally not in detail. I know that there are projects going on, people studying this. The situation in the field is such that people have proposed algorithms in various areas, including fusion, including chemistry, calculating binding energies, including medicine, and so on. But nobody really knows how these algorithms scale. And basically because it's a remarkable fact that if you go over 50 qubits or so, even the best classical supercomputer can no longer simulate the system. So you basically can't predict how things will scale. So we are really in the situation where we are burning to build hardware that is large enough so that we can test out these algorithms that have been proposed to figure out, how they basically, what the scaling properties are. Remarkably, Shor's algorithm is the only useful algorithm that we know of where there's a mathematical proof that it will work if you make it well enough. For all the other algorithms, they are just proposed, and we have the hope that some of them at least will work, but we don't know. But that's one of our reasons to drive the hardware to be big enough so that we can at least figure out the scaling. Will this solve the particular problems in plasma physics, for instance? Better than a classical computer, and you really need something like an exponential speedup. If it's just a quadratic speedup of some sort, it will not be enough, at least for the foreseeable future, to compete with classical computers.
Because the classical computers have a real problem when you get beyond one dimension. I mean, they can do a little bit in two, but the classical problems are really three-dimensional problems, and as an experimental scientist in plasma physics, I was always asked questions about what the theorists were doing, and I always said, well, they're working in one dimension and we have three.
Yeah, so these are really open questions, and we are looking forward to hopefully being able to address them.
Thank you. All right.
Steve, we have questions here, and then we'll get to you.
Yeah, I have three questions, if you don't mind, and I'll take them one at a time, if you don't mind. First one is, I've heard that some people are trying to do quantum computing just with the nucleus, in other words, nuclear spins. Is that true? And if so, where are they in this development?
So I'm not quite sure what you're referring to. If you can certainly store quantum information in nuclear spins, and nuclear spins are very good because they're very isolated for the environment. So to store quantum information, there are experiments going on, and indeed nuclear spins are the best. This number that I mentioned of 30 minutes or so storing quantum information was actually done in nuclear spins. However, to do interactions, you need to couple them to something else. Interactions between nuclear spins are too weak. So I'm not sure which experiment what they use.
Okay, yeah, what I'd seen was that there were some experiments where they were trying to make quantum computers by coupling or entangling nuclear spins.
Right.
But you say that the interaction is too weak for entanglement, apparently. So that's probably not going to result in anything.
Well, then the experiment that coupled the nuclear spin to an electron spin for the entanglement and then go back to the nuclear spin. In solid-state systems. So that is possible. In solid-state systems, at the moment, all experiments are not scalable. The environment is too dirty. There are too many impurities and stuff to really scale it. But there are ways people are trying.
Okay, so there I go. Second question is, when I did my thesis work, I did a lot of work in excitation and emission and so forth. And we didn't do Rydberg states, we were doing molecules. But one of the things at that time was trying to understand the phosphorescent state. It looks like a lot of information that I'm not aware of yet. You're actually taking into account here when you're having these Rydberg states where you can store this information for a long period of time, which is the whole secret to a phosphorescence where you didn't have the coupling where the de-excitonilures, you didn't have fluorescence, you had phosphorescence with the spins of the electrons. I'm not saying it correctly here, but the electrons are not paired, or they pair incorrectly. So it was a state that wasn't supposed to exist. It was a non-existent state, and that's where phosphorus came from. Well, it looks like what you're showing here is that you're actually getting to that. And you're explaining what phosphorescence is. Is that correct?
It's interesting. I don't understand the system that you're talking about enough to make to make a clear statements. What I want to emphasize is that while we use the Rydberg state for the gates and the interaction, this state itself is unstable. So we never store quantum information in the state. We always store it in the electronic ground state. So we just briefly guide the atom for maybe 200 nanoseconds to this Rydberg state to induce the gate, and then quickly go back, as quickly as we can, go back to the ground state where the information is safe. So I'm not sure how that will look in your system.
Yeah, okay. So what's happening is your omega in blue here is probably going to what we would have called the fluorescent state because it was unstable. Yeah.
Yeah,
I think
probably.
that's what's going on. Third question, and this is a dumb question. How do you do a calculation using quantum computers? I have an idea of how you do it with regular digital computers, but how is an actual experimental setup done so you're doing an actual calculation with these quantum computers?
Right. So maybe in this movie I can show a little bit the idea. So there are a few steps involved. You first need to initialize the atoms, say in all this zero state. We do that by a laser pulse, what we call optical pumping. This is also something Dan Klapner worked on. So basically, if you excite the atoms out of the one state with a laser beam, eventually they fall out in the zero state, or fall into zero state. So the first step is this initialization of the atoms in all the zero state. Then come these various gates between the atoms, these quantum gates. Each of these quantum gates is basically a laser pulse of this blue laser that I showed before that puts atoms into the Rydberg state and uses this quantum gate. There's a particular sequence of these gates. So what you show here symmetrically is, certain types of gates are induced. And then the final step is, after you're done with all the gates, is you use again laser fluorescence to read out the state. And you can arrange things in such a way that, say, the zero state is dark, so when you turn on a laser, the atom doesn't fluoresce, and the one state is bright, so when you turn on the laser, it does fluoresce. So there are really 3 steps involved: initialization, which is done with lasers, the computing step, which is done with lasers, and then the readout, which is done with another pair of lasers again. It's kind of remarkable if you think about it. We build this quantum processor, so we perform one calculation, and then we throw all the atoms away. And then we start with a new bunch of atoms. But, because, 1 gram of atoms contains whatever, 10 to the 20 atoms or so atoms are cheap, we can actually afford to do that. But these are the 3 steps of the computation. It's the assembling the array cloud in a particular pattern here, initializing them in one of the quantum states, performing the quantum gates, and then using fluorescence again. So everything is done optically. There are no wires going in here. Everything is done with light. You control all the steps of light.
Thank you. That really opened a big door for me. Thank you very much.
That was a good point. Steve?
Okay, I'm expecting that I'm going to show my ignorance here, so please bear with me. I'm familiar with classical computers, and I know what a core is and how it's represented digitally. Its value, it depends upon which way the magnetic goes. What I'm trying to get my hand around is a number of the concepts here and how they fit together. And I hope I'm not talking at too low a level for you, Vladan, but that's the way I'm working right now. How does a qubit compare to a bit?
So the only difference is that you can be simultaneously in both states of the bit, right? In a classical bit, you're always in 0 or in 1. Mm-hmm. In a qubit, you can be in both 0 and 1 at the same time with varying amounts, right? So you can be halfway between 0 and 1, and even then there's this extra phase. So basically, there's, if you think of it, there's more degrees of freedom. The bit are just like 2 points, but this qubit is this little sphere that I tried to show in the very beginning. So basically, a qubit can be in any of the states described by the sphere. So the bit has only this 0.0, I say up, and this 0.1 down, and this quantum system is richer.
So the power then of a then the power then of this is that while a regular bit can be only 2 states, a qubit can be in many more states.
Yes, that's part of the power, the fact that I can measure, you know, along any axis, right, and can be in many more states. But probably people don't really fully understand, but you know, it is believed that the most of the power actually comes from this entanglement feature, that these quantum correlations can be stronger than the classical correlations because they can persist in different bases. So if I have 2 bits,
how does
yes,
go ahead.
Yeah, so basically, if I have just 2 classical bits, right, I can correlate them, right? I can make them say both 0 or both 1, right? But in a quantum system, I can make them in a more complicated way. I can make, you know, this one, you know, both 0 and both 1, but with a, that if I measure along another axis, they're also both 0 and both 1, or both 1, for instance, which is impossible classically. So it's partly that I have this more states, but also that quantum, this is this famous Einstein paradox. When Einstein tried to describe everything classically, he came up with a limit on how correlated things could be. This is this famous Bell's inequality, you know, this kind of root less than 2 correlations for classical systems. So for quantum systems, the correlations can also be stronger. They can, because they can persist in different bases.
And why is the entanglement an important part of this? Why do we need to have the entanglement between these 2 atoms?
To make full use of this power of the correlation. So you can think of what is a quantum computer doing. It's actually performing many different computations at the same time, because, you know, you start with some superpositions of states, right? Some different possibilities, and then they're all evolving simultaneously and coming back together in the end when I'm doing the measurement. So the entanglement is what allows one to perform, to go all along these paths at the same time. Let me try to give you a picture. Imagine that I have two dice, okay? And somehow the dice are magically, you know, somehow set up so that you throw them separately, but whatever the first dice shows, the second die also shows. So each of these dice is kind of, you know, randomly selecting between 1 and 6, but entanglement makes it in such a way that they always show the same number. And that's something that's impossible classically, but is possible quantum mechanically.
And how does that play into forming a computer based upon atoms being in multiple states and entangled?
So what that means is that to describe an n-bit quantum system, you need many, many more possibility to describe it because of this possibility of entanglement, because you have all the possible combinations. So to even store 100 quantum bit system because of these many possibilities and the possibilities of correlations would be more information than is, say, contained in the entire internet, just for 100 quantum bits. Because you have to store not only, you know, what are the states of the particles, but also what are the correlations, meaning what happens if I measure this particle in this state, what is the state that I expect to measure for the second particle. This is the correlation. So if you think of it as a matrix, basically you have many, many more entries in this matrix because of these correlations or this entanglement compared to independent systems.
Okay, all right. I'll let somebody else answer the question.
Would it be 2 to the 100?
We have, Carl, there's a question here, and then we'll get back to you if you don't mind. Jerry?
I wanted to ask, with the use of lasers and varying energy states, how do you maintain microkelvin temperatures?
Okay, very good question. So the atoms are first laser cooled. When you shine in the lasers, you just propel the atom to the upper state and then you bring it back down. So the atom doesn't actually scatter any light or does anything. It just absorbs 1 photon from the laser beam. I'm trying to find correct picture here. And then it puts that photon back into the laser beam. So it's an interaction which is basically just taking one photon out and putting the photon right back into the laser beam. And in the process, it acquires phase in the system. So it's not like for these lights.
So it's a zero sum. So it's a zero sum?
It's a zero sum, yes. Mm-hmm.
You're good, Jerry?
Yeah.
Okay. Carl?
Yes. So my vague understanding of quantum computing is this idea that a qubit can essentially represent many states because of this thing of, it can be a little bit zero and more one or the other way around, etc. Is this at all like analog computers that we're pretty much displaced by digital computers? And how is it different?
That's a very good question. It goes back, it's hard to explain for me. It goes back to the previous question. So a single qubit is like analog computers, but this ability to make entanglement, which are really quantum correlations, is something that you don't have in the analog computer system. So if I took, 2 bits and tried to make each one, some kind of dial like an analog computer, I could not make this entangled state between them classically, right? So there's no classical way to represent with analog computers, with analog spins, this quantum system because of these much stronger correlations that persist in what we call any basis, any measurement along this direction. So it's analog computing plus the power of quantum correlations. The analog computing is actually the part we don't like, right? Because analog computers fail because there's no error correction, right? You have small errors and then they propagate. This is what is trying to be fixed by this quantum error computing, quantum error correction schemes, right? But it's really 2 ingredients, analog, and it's believed that analog is not the fundamental part. The fundamental part is believed to be this correlations, these much stronger correlations in the quantum system than in the classical system of analog particles or analog bits.
Okay, thanks.
Ted?
Thank you. So after all of this is said and done, I mean, you've said you've got a company. So obviously you hope to sell either the processors themselves or service on the processors. If it's service on the processors, how do you connect to the processor over a network of some sort or other? And I presume that maybe AWS might be interested in that, I suppose. And there's also, people talk of the quantum internet that is being tested in various places. Can you relate these things together in some way?
That's a very good question. So for how to use it on a network, there's no quantum internet involved, right? I mean, what is happening already is the user sends their gates to get performed, the information about their gates to AWS, and then AWS relates this to Quera, and then Quera, there's a compiler that takes these logical instructions and turns them into, what laser pulses need to be turned on, right? And there's the readout, and then this classical information in the end, what is the state of each bit at the end of this computation sequence or simulation sequence is sent back to the user. So the input output is classical. You just, as a user, you say, I want to, arrange the atoms in this particular pattern. I want to perform these types of gates for, this number and this amount of time, etc. And then what is the final state of the quantum system? So the input-output interface is purely classical. That's how it works. And then everything is, quantum is done within the machine with the laser pulses. The quantum internet, which is really its infancy, is the idea that you can send quantum states via the internet. And the main thing is that this could be potentially secure and against any eavesdropping. The basic idea is that if I send, either electrical pulses to you or maybe light pulses over a glass fiber, that travels as you're watching my Zoom talk, right? Anybody could take a little bit, small portion of that light pulse and read it out, and you would never notice because there's even noise on these pulses. But if this information is sent with just a single photon from me to you, then if if somebody steals the photon, you will notice it immediately, right? And if somebody tries to copy the photon, the rules of quantum mechanics forbid the cloning of quantum states. So there are measurements that you can do to determine whether somebody tried to copy the photon information or not. So these are related but somewhat independent fields, right? In one case, we're just trying to do, secure quantum states, quantum information. In the other case, the input-output interface is always classical.
Vladan, I just as you're talking here, I'm sorry, Ted, were you finished?
No, I just had one observation that is kind of silly, but the sort of icon of the Paris Olympics was the Eiffel Tower with all sorts of accoutrements attached to it, either virtually or reality. Did the Paris group do anything to highlight the fact that they had made an Eiffel Tower using the qubit structure?
Not beyond that I'm aware beyond this paper. So they just wanted to show that they can make arbitrary structures in 3D with light beams. And they haven't actually used it for anything.
No, and well, I wouldn't think they'd use it, but they could highlight it as because I know they did a lot of showing off of what they had accomplished in Paris in all sorts of ways that had to do with animations and things. I thought maybe, throw out something here too.
I don't think they were on the Olympiad. I haven't heard.
No, not.
It would have been a good idea, actually. So.
Get a few francs, or actually nowadays euros, maybe from the French government to support it. But thank you.
Thanks, Ted. Vlad, just as you're going through this, and I'm gonna mimic what Steve said, is that I'm gonna display my ignorance. Is you use the word code on many of the slides. What is that? And I'm a classical computer coder. I'm a software engineer. What does code mean in this environment?
So code means pretty similar to classical computers, means a sequence of gates. Only the gates are a little bit different. In the classical computer, at the most basic level, you have these logical Boolean gates, right? And or gates. For us, code means something like this picture here. So what this picture represents, each of these lines is a logical qubit. And then each of these connections shows a particular quantum gate, a particular interaction being performed on some pair of logical qubits. So for instance, here we take the logical qubit number 1 and the logical qubit number 6, and we perform this controlled NOT gate that I tried to describe. And then we do this for the same for the qubit number 2 and the qubit number 7. So for us, code is a set of quantum logical operations. So in that sense, it doesn't differ really from classical codes, where you also take particular bits and make them make at the most basic level interaction logical gates between them.
So the logic is Boolean?
Sorry?
So the logic is Boolean?
It's similar to Boolean. It's the quantum generalization of Boolean.
Yeah.
If you want.
Can you sort of explain what that means? Because to me, again, my naivete, Boolean is binary. Mm-hmm. And when you say quantumization of Boolean, it says sort of a square circle. And I'm sort of confused.
So it turns out that if you specify what happens for each of these, just for the state 0, 0, and 1, if you specify what happens for each of these combinations, which looks very classical, right? I could do this on a classical computer, right? If you specify what happens to each of these combinations, then you have specified also everything else that happens. You have also immediately specified what happens if the first bit is not in the 0 state or the 1 state, but say in a superposition of 0 and 1. So it's a set of rules like this that I call the generalization of Boolean. So it's certain types of combinations of two gates performed. But I allow this to happen also for superposition states. And basically, if I have a superposition state for the first qubit, then I get a superposition state for the system. Does this kind of help, or?
I'll leave it at kind of, because I need it to settle. Thank you.
Superposition of Boolean.
Yeah. You know, I could get into a course on this because it's slowly working its way through the rust between my ears.
So what you're doing then is extending the Boolean system of logic so that you can have these superimposed states.
That's exactly right.
The superposition.
It gives a yes or no answer in a full paragraph form.
Exactly. It's a long yes or a long no.
All those masters. No.
Yeah. Steve?
Could you liken a qubit and a quantum computer to thinking back a long time ago, before digital computers, there were analog computers. Then when they went to digital, they said, well, it's a lot easier if we work with 0 volts and 5 volts, or 0 and -5, whatever it is, so that we change the value and then we see whether it's closer to 5 or closer to 0, so we get a 0 or a 1. Now, with an analog machine, you can have many different voltages, 0, 5, 10, 20, 30, 40. Is it possible that we could liken the way the quantum computer works to the way an analog computer might work, where a given state might have many different voltages?
That's a good question. It's similar to the question asked before. So one qubit could be represented in this way, right? One qubit could be, a range of voltages, or maybe you would actually need a, two-dimensional matrix, right? You could take, these states on the sphere and, describe it by two numbers and then do it analog. So one qubit could be a two-dimensional analog system. However, as soon as you use quantum interaction, and particularly these quantum gates between them, there's this class of correlations that can never happen in a classical system, because a classical system cannot be simultaneously 0 and 1. So it is not possible already two-qubit system you cannot represent by two analog numbers anymore as soon as they are made to interact.
But could you say that if you have a voltage 0, it means 0, voltage 5, it means 1, voltage 10 means it's both 0 and 1?
Yes, but then you are forced into an exponentially large space. So if I want to describe n qubits that have possibly quantum interact with one another, I need a 2 to the n large classical space to image that. That's the problem of it. That's why it's not even possible to store the quantum information anymore on a classical computer, let alone do computations with it. So basically for 100-bit qubits, you need 2 to the 100 bits, which is about 10 to the 97 or so. Some 2 to the 100, sorry, 2 to the 3, 10 to the 30 or so bits, right? So basically, this exceeds even the largest classical memories. And that's because of these quantum correlations.
Yeah, so it becomes just unfeasible to do this kind of calculation with classical computing and with the architectures.
Right.
Can I ask a quick question along the same line here? You're talking about going from the ground state to a specific excited state, right?
Yes. Mm-hmm.
In these Rydbergs. Could you go to another excited state? And could you use that? Could you go to the second, third, fourth, and use that somehow to increase the ability of these computers to do the computations?
Yes, you actually can. And so different states have different strengths of interactions and different ranges of interactions. So indeed, people have started doing that. So basically, if you go to a certain state, it will interact with a certain strength. And for a different state, it will interact over a larger distance.
See, Mike might.
So this state up here is some high principal quantum number state. And when you change the state, it will interact over a different distance. I haven't had time to show things, but we have actually done this. So if you go to a lower lying state, it will maybe interact with just the neighboring atoms. If you go to a higher lying state, it will maybe interact with a larger group of atoms within that range and so on. So indeed, that's a...
So the different states have distinctly different patterns of interaction, which could be separated from each other and make even more power in the computing.
Correct. That's correct.
All right.
They have both ranges and also directions of interactions, depending on which state you go to.
And you can observe all that, and you can use that to determine what the result is of the, I'm going to call it, calculation.
Yes, you can. And thanks, for instance, due to the work done also by Dan a number of years ago, we understand these states very, very well. They are very well described by these quantum models of states, so we understand how they interact, how strongly they interact, etc.
So the outputs of each of the states can be distinguished readily from one another.
Definitely, and people have done that.
Mike?
I have an experimental question, of a very elementary sort. In modern computing, making things smaller has become very important. What's the size, a typical size of this, and what are the expectations of making them smaller? The size, I mean, of your experimental setup.
Right. So, the atoms themselves are very small. As I say, kind of hair. Think of this whole thing as 200 microns or so. So basically, the processor itself, even a large processor will fit on a millimeter square. The vacuum chamber is, there's a glass cell and some pumps. It's roughly this size. That could be miniaturized further, probably to the centimeter scale. What you need to do is you need to keep glass surfaces away from the atoms, so they can't be closer than a few millimeters. That's kind of the physical apparatus. But the biggest size in the system is actually the lasers, because at the moment we use science-grade lasers, which are, kind of big and bulky, although people have already done setups where, all the lasers are packed in, say, one rack, kind of, the size times, maybe 6 feet. So the biggest physical size is actually, the laser packages, because there's, half a dozen at least lasers involved in these systems to laser cool the atoms, to observe the fluorescence, and then to induce these Rydberg interactions.
So the largest challenge is getting the lasers smaller.
Getting the lasers smaller, and also in some instances more powerful, while controlling their frequencies very, very well. So for, in this experiment with, 6,000 atoms, a laser was used that had, 50 watts or something. So these are almost, not quite yet welding strength lasers, but they are, very powerful lasers already. But they also need to be very well frequency controlled. So making the laser smaller, more robust. And honestly, the thing that fails, that we need to replace in these systems, every 6 months or a year or so, are actually the lasers. Everything is very robust. It's kind of interesting because there are no wires, there's no electrical system crosstalk in these things. Everything is with lasers and they go through one another, but the lasers are, in some sense, the biggest technological challenge.
Thank you.
What's the state of the art of the lasers? Are those lasers coming down in size and being more controllable? Is that something in the near-term future?
Yes, so most of the lasers have come down in size, are small. So the ones for laser cooling, etc., are small. Also, the lasers that drive these transitions. The one where we want high power is this blue arrow. That's the laser that excites the atoms from the ground state to this highly excited state, basically because that sets the speed of the gate. You can see here a typical time scale. This is 1 microsecond. So maybe a gate takes 100, 200 nanoseconds. And the faster we can make this gate, the better these gates become. So the main challenge is to make these blue lasers very powerful, at the same time very stable in frequency, so that we can drive these gates with smaller and smaller errors. Because the further we are below this threshold for logical bits with our laser induced, the errors are mostly laser induced. And they are coming down. We are working with companies to make these lasers both more powerful and more precise, or having less frequency noise. But that's one of the technological challenges there.
I'm surprised you haven't talked about cooling more than you did. It seems like keeping this whole system very cold would be a challenge. It takes a lot of equipment.
It's actually simpler than you think. When you walk into a lab, nothing is cold except the atoms themselves. Everything else is at room temperature. So you just shine in some laser beams, and these laser beams for cooling nowadays, they are kind of moderate, they are kind of laser pointer strength. If you have a very powerful laser pointer, that's the strength of the lasers used for cooling. They are, of course, much more frequency controlled, etc. But the cooling lasers are really not a challenge anymore. Laser cooling was invented now, almost 40 years ago or so, 30 something years. So that's not the difficult part of the system. And you wouldn't notice that anything is cold because it's just the atoms that are, just a smidge above absolute zero at very cold temperature. Everything else is at room temperature. So there are no refrigerator, cryostats, anything like that involved in these systems. It's just the glass cells.
Laser cooling blows my mind. When I think of lasers, I think of light and I think of heat. So when you talk about laser cooling, it doesn't work in my mind.
I got it written down to look up. Don't worry.
So you think of lasers as powerful?
40 years I do.
I'm sorry?
We think of lasers as powerful, but you think of primarily of them as orderly. Lasers have extremely small amounts of disorder, right? All the photons are in the same state. So in physics terms, you call it entropy, right? But lasers are incredibly orderly. Even if they are the most powerful lasers, they are very orderly. And so we can use this orderliness of the lasers to take some of the entropy, some of the disorder, the thermal disorder out of the atoms and put them into the scattered light. That's the basic idea.
Still
Magic.
Yeah.
Magic. David?
still don't get that part. I should focus.
David Kahn?
Oh, yeah. Hi. I was just sitting here
Yeah.
thinking,
I still don't get why they cool.
Can you hear me?
Yes.
Yeah.
we
So
can.
anyway, I'm sitting here thinking of Star Trek. So are we going to see portable quantum computers like sometime in the future?
At the
Next
moment,
week.
At the moment, these are a little bit smaller than the rooms filled of vacuum tubes in classical computers, right? They are kind of, at the moment, the smallest you could get is maybe, half a dinner table worth of optics, and then maybe a rack worth of lasers and electronics. But if we can miniaturize the laser systems, which in principle is possible, right? That's where you could imagine, something not maybe quite desktop size yet, but starting to be on that scale. Of course, at the moment, these things are very expensive. The cost of this is maybe on the order of 20 million or so of the whole complete system.
All of us are old enough to remember analog computers and using a slide rule. And the thing that really disappointed me is when you go through solving all these differential equations or you try to put it into an analog computer, what do you see? A sine wave. And that didn't impress me, and it impressed me negatively. And then when computers came along, I said, finally now we're working with dx dt, the bits. We can differentiate them and we can integrate them in the digital computer.
Mm-hmm.
So you see my point? We're getting there slowly but surely.
Yeah, you can see the quantum is really in between because we can make them, we can plot these oscillations. So they perform like an analog system. But when I actually read it out, I never see 0.5. 0.5 is just the probability. What this, kind of sign means that is 50% of the time I measure 0 and 50% of the time I measure 1. So they're kind of a weird mixture in between. Any measurement that I do is always a 0 or a 1. Right. It's just that, in the end, the probabilities is what is plotted here in these oscillations. But the outcomes are digital. But, the main advantage of digital computers is that you can correct errors, right? Which you can't do on analog computers, right? And here people have figured out a way, albeit complicated way, to correct errors in quantum systems.
What other technologies, quantum technologies, superconducting circuits, various other technologies do you think is the principal competitor to your quantum computing technology?
Yeah, so the oldest quantum computing technology is ions, trapped ions. It's somewhat similar to the neutral atoms, but you use charged particles that you can hold on to more easily. They were the first one. They are not quite as capable in my view as neutral atoms to scale up to large numbers, but they are interesting. The second competitor is superconducting qubits. Google, IBM, they are betting big money, and they've spent, probably $1 billion or more on this. They like it because, it involves fabrication and so on, but there the challenge is that atoms are natural qubits. Qubits need to be identical, exactly identical. And when you use atoms, they are kind of identical by definition. Two rubidium atoms that we use are exactly the same. Whereas if you build, effective qubits, you have to make, very, very tight fabrication tolerances. So these are the two serious competitors. At the moment, kind of, I would say superconducting and neutral atoms are neck to neck. There's also photonics quantum technology. I would say this is the technology with the biggest promises and the least realization so far. This is to use photons, and there just the challenge is, photons have losses. How do you make these robust systems, with hundreds of thousands of photons? The photons are kind of at the moment at the level of 10 or so is the biggest things people can make, and even these are not, entangled states, etc. But I would say superconducting qubits and ions are the two competing technologies.
Thank you very much. We appreciate your time. And
thank you so much.
It's been a really great presentation. Thank you again.
Thank you. It was a great pleasure to interact with you. And thank you, Dan, for inviting me.